more place on my website, so it's coming up right now. It's a little small because I got dual screen, but the first one is review of covalent, ionic, and metallic properties, and the second thing is a little simulation on my links from my web page, not simulation of multiple choice of practice. So finish that operative and then move on. Something after that? Thanks, Nick. Alright, put your hand in the air if you're done with soccer tube. Okay. Put your hand in the air one more time if you're done with soccer tube. You are done with soccer tube. Okay, great. And then so either one, I don't care which one you guys move to next. Either go to the solution solubility quiz, which is a multiple choice thing on my website, so it's like the third link down or so. Talk to your table groups. It's a totally open response. Just make sure that you ask me questions on the solubility quiz if you don't understand what that question's asking. And then we're going to kind of hit up some of those together. So do think, brainstorm on those. Take one more minute on soccer tube. So 1 more minute. That should be quick. Alright, I'm cutting off Socrative. We should have had plenty of time for that. So you guys are here. Give me a thumbs up if you're doing okay so far. I want to see, like, you know, maybe a handshake if you got a couple of those wrong. And I'm going to take some of those questions at the end, which ones that you know that you're like, I don't know how this is right or why this is right. You also can talk to your lab, your group mates, your table mates. Because you're quiet as can be. Sounds like you're yawning. In the middle of practicing those solubility curves, let's go through a couple of these and you guys tell me what you did, what you saw, what was right, what was wrong. That way we have a chance to kind of recap this together, okay? So for this one, my questions might be out of order based on yours, but let's just quickly move through these and just get ready because I'm calling on one of you guys, okay? Ready? All right, so which of these salts decrease in solubility as the temperature increases? Looking at your graph, potassium nitrate, cesium sulfate, potassium dichromate, or potassium chlorate. The cesium one, right? It's the only one that's dipping down. So cesium? Yeah, 100%. Nice, guys. Next. As a solution of potassium chlorate is 20 grams of salt dissolved in 100 grams of water at 70 degrees Celsius. Approximately how many more grams can be added to the solution before it reaches saturation? So saturation means what on this graph? Where does saturation, like if you're looking at a graph, how do you know it's saturated? It's on that line, on that solubility curve line, right? So if I'm not looking at potassium chlorate at 70 degrees Celsius, everybody look at potassium chlorate at 70 degrees Celsius and tell me what the saturation point is first. Robbie? So potassium chlorate's the red line at 70 degrees Celsius. You draw the line up, it crosses right at 30, right? So 30 grams will dissolve just perfectly. And so if I have 20 grams I've added, how many more can fit in there? Another 10 more, right? So we're down here. And if I just kept 20 in there, what kind of solution would that be called? Everybody. Unsaturated, not saturated, right? So it's undersaturated. So I can add 10 more and I'm good. How are we doing so far? Okay, we learned some of this yesterday, but this also is like introducing that there's more questions that could be asked from a solubility curve. All right, so a solution of potassium chlorate, sorry, not next. When 30 grams of potassium nitrate is dissolved in 100 grams of water, the solution can be correctly described as, so you're looking at potassium nitrate at what temperature? Potassium nitrate at 20 degrees Celsius, and how much can dissolve? It happens to be 30 again, so it's easier to see on your screen than my screen. Okay, so 30 can dissolve, and we put 30 in there, so what do we have? Thank you. Let me get that one more time. What kind of solution do I have? Everybody? Saturated. All right, so stay engaged with me here, okay? And then least soluble, what would you be looking for? Maybe this back table right here, mixed table, what would you be looking for? Okay, at 0 degrees Celsius, right? And this happens to actually literally be on the y-axis. So who's that here? Don't spell it for me. Name it. Come back to me. This group. Not sodium. Potassium chlorate, right? Potassium chlorate would be a nice. All right. A beaker contains 80 grams of lead-2 nitrate and 100 grams of water at 30 degrees Celsius. How many grams are undissolved on the bottom of a beaker? Let's go Jillian and Lindsay's area, that table back there. Tell me what you're thinking about, what you're doing as you go. So 80 on the y-axis of lead-2 nitrate. Okay, so lead-2 nitrate is here. And at 80, I'm sorry, I'm going to have you, when you say 80 on the y-axis, where am I on the x-axis? Okay, so I'm gonna start with the 30s. So 30s where we're supposed to be, right? So 30, a solution of potassium nitrate at 30 degrees can dissolve how much? Everybody answer this. About 65, 66, right? So it can saturate at 66, but if I add 80, that's oversaturated or supersaturated, so not all of it will dissolve. And so she said the difference between that line was about 15, 14, and so that answer should be 14. Okay. I'm going to stop there. Are there any other questions on there that you guys were like, I don't know what it's asking? Speak now for which piece? Okay, I'm going to stop there then. I hope you've had enough chance to practice with that. Let's go ahead and bounce to a couple of notes that relate to solubility. Then we have actually 2 labs we're going to do. One lab is finishing up your endothermic, exothermic, thermodynamic stuff from yesterday. It's just kind of like the final cap that I want to put on this. And then one other one's related to solubility. And so we're going to work with that shortly. So have a piece of paper out or your notes from yesterday. We can add to that. And then before I do that, sorry, I did have this third warm-up. I'm going to ask for a couple of people to shout out some answers for different types of properties or examples that you remember from ionic, metallic, and covalent. So right now at your table, come up with at least 5 things. You can go anywhere on the chart. Talk.
Ionic,
All right, so I'm going to bounce around tables. If you want to establish one person be the talker for ionic, one person covalent, and one person metallic. I, C, and M. I, C, and M. Figure out who's who. There's 3. All right, and you're back to me. You should have decided. First group up here. Ionic, give me a property. Ionic, give me a property.
low melting point.
Lies. I'll come back to this group. Maddie's group. Say again. I can't hear my people. High melting point. Okay, like high, like 1,000 degrees Celsius, like pretty dang high. Robbie's group. Ionic. Say again. When you say conducts electricity, what state of matter would it need to be in? Say again. Aqueous, right? So aqueous solution. It will conduct electricity. You should be writing these down with me. This is a good review of ionic, covalent, metallic, and so forth. EJ's group. Usually it's a metal and a non-metal together. But we discovered one yesterday or the day before. What was that example that was not a metal, non-metal? 2 polyatomics, right? So I'm going to just say 2 polyions together. Definitely ionic because we got polyatomic ions, right? Lindsay's group. Weber. Your little area, ionic. Ooh, nice. Valence electrons are transferred, not shared, or I'm going to say another word for that would be donated, to form that bond. And then Julian's group up here. All what? Electrolytes. That's a wonderful word for that. Okay, so these ions equal electrolytes. Who's ever heard of electrolyte? Gatorade or Powerade, right? So you're drinking these electrolytes to refuel yourself. It's not about the energy. It's not about carbohydrates and sugars. It's about giving your body ions back because the ions help with electrical conductivity in your body. Why do you need electrical conductivity in your body? What uses electrical conductivity, Robbie? Your nerve system. Well, that might be important for sports, like some coordination, right? Or for energy or movement at all. What else uses a form of electricity? Anybody know that? No one's taking it out of me? Yeah? Okay, so your heart is definitely like the pump of creating some sort of electrical impulse as well as a pump for blood, but it's also your your muscular skeletal system, meaning like the muscle fibers have an ion exchange, which makes your muscle contract. The ions exchange again, the muscle relaxes. And so if you don't have ions to exchange, you could be really, really tight. You could have contractions that wouldn't go away. It also means that you wouldn't have any ability to contract. So there's many things that use electrolytes in your body, so you do have to refuel when you sweat. I got one more group up here, ions. Ionic.
I was going to say the electrolyte.
Do you have anything else you can add?
Salts.
Okay, good. A good word for that. Cameron, put your phone away. Salts. Okay. And coming back to this group over here for covalent. Give me something for covalent, front group.
Low melting point.
Wonderful. Okay, so this one has a low melting point, whereas ionics have a high melting point. Caleb's group? Four conductors. Good. And that's going to be true at all states of matter, solids, liquids, and gases. Margaret's group? Two nonmetals, usually together. Great. Nick's group?
Low conductivity.
We already said that.
Low diffusion and vaporization.
Okay, so low energy needed to melt or vaporize. That really connects to low melting point or low boiling point. So I might come back to you guys, ask for another one in a second. Audrey's group. Okay, so valence electrons are shared to make a bond. Wonderful. Kim's group. Okay, guys, we said this word. It starts with a V. It's what makes you smell good. Volatile, right. So volatile means that it evaporates really easily off your body. And so that word, which connects to, I think, what Chloe's group was saying too, it means that it vaporizes easily, which makes your deodorant make your body smell good, right? That's why deodorant's got that waxy kind of feel to it. Anything else you guys can add, this group? Sorry, I got you the nitpicking here. Okay, well, I'll come back to you guys. I'll start with you guys in the next one, okay? Anything else? Mm-mm. Does a candle conduct electricity? Mm-mm. Does some oil? Mm-mm. Nothing really. Our only ionics will be great conductivities, but I'll come back to metallic for you guys first. So let's give an example. I did have salts over here. Salts were ionic. Can I give an example of a salt? Shout it out. Don't say sodium chloride, that's overused. Okay, potassium chloride. You guys are cheap. Okay, give me an example of a covalent structure. Okay, water. Good. Can I get something else? Nitrogen monoxide. Look at that. No. Something else? Don't spell it out. Thank you. You guys have to use your brain. Can I get another ionic? This side over here. Calcium chloride. You guys are cheap. Give me something other than chloride. This group over here. Kyle's got you. Say again?
Sodium nitrate.
Sodium nitrate. Can you tell me that formula? Can you tell me that formula? Wonderful. Okay. So we got a good idea of ionics and covalence, right? Back to metallics, starting with the front group. Give me a compound property.
They're conductors electricity well.
They conduct in what state of matter?
Solids.
As solid, and if they were able to form liquid, it just means which to melt a metal, which can happen. It's just going to be a little bit rough. It can conduct as well. Carson's group.
Malleable.
Malleable. Love it. Next group. High density generally, which means that do they float or sink on water? You dropped a penny in water. Likely will sink. That's why they have those wishing wells, right? They sink. That people can't steal all the change. Emily's group. They have an interesting way of sharing. We call it something a little different than sharing. Say again? Sea of not only just plain old electrons. We have another word to say that the electrons are kind of just delocalized. Okay, that was a 3-group effort there. Okay, so sea of delocalized electrons.
Miss Emma,
Yes,
do you have Justin Snyder in there?
I do.
Can you send it to the nurse when when you can?
Yes, ma'am.
Bye,
Thank
bye.
you. Okay. Kyle's group. No, I kind of got delocalized from you guys. Coming back. Kim's group. Not soluble. If metal dissolved, you would be eating your soup, and then the spoon just goes away. That would be awful. And then it'd be toxic, and then we'd all die. No one could eat soup anymore. Okay, not soluble. Can I get some from maybe some groups right here then? Anything else? There are like 2 more things I'm looking for. Shiny, lustrous. Let's use our big boy terms. I don't know what that sound is. Lustrous. It's like, great idea, Nick. Okay. Can I get one more? Shout it out. Awesome. Okay, so high melting point, just like ionics have a high melting point. A couple more. Ductile, which was usually given to me with malleable, but we got that now. One more. Hard and dense. So we kind of got the density thing already. I'm going to say hard and also has a lattice structure. Lattice and hard. Anything else? Can I get some examples? Let's go, Darcy. You seem really awake. Examples. Iron. Okay. Can I get something else, Bernice? Magnesium. Something else. Miles. Copper. Those are great examples. Okay, so I feel pretty good. You guys have a great memory, actually. You did a good job in your groups. That's a good review of those. This is like, I swear to you, you'll see like 3 questions like this on the final exam about like what are the properties of metals and properties of ions and differences between them. It's so important to understand like the mere differences. And today we're looking at the differences of compounds similar to this, but in solution, not really just inherently by themselves. So we're gonna look at them in solution. All right, so I've got like 2 more things for us, and then we're gonna go into the lab, okay? Justin, they called for you to the front office, to the nurse. When you get a chance, go to the nurse. Okay. All right, so take I don't know, 2 minutes or so. Draw your picture. It can be anything. It can be a comic. It can be something that's kind of what's the word I'm looking for? Dry humor. It can be anything that would help you describe the difference between solute, solvent, and solution. Draw it on your paper. It's a quick creative thinking. Has something really good brewing. I'm going to try to do my demonstration for you. I'm very neat on this, but it's required. It's okay. It can be okay. So I'm not exactly sure this is going to work. Can you guys look at there? I'm trying to how it works. There's no work. There is not practice here. My experience for you is really just pure magic, okay? No chemistry, pure magic. So I have some water here, POC. I have some solution. No promise this is going to work, okay? So don't judge me. I broke my flask yesterday and everything went everywhere. And I really tried again, but it takes a lot of effort to make this work. So, cross your fingers. You make your twirl. Okay, so. No, it's good. Okay, ready? With the top of my magic wand, I'm going to solidify my solution. So, I'm going to come back to my demonstration. Let me try this other one first. Free mind for about 30 seconds there. Don't talk to me, it works. It works. I have to, like I said, magic doesn't always work.
Oh yeah, it's gonna go right.
So Justin and I both messed up. It's not just me. You guys can blame Justin too. We just didn't think well together. With the top of my magic wand, I'm going to solidify my solution. Cross your fingers. Alright, and you can feel it. Breathe. Feel it. It's not, you got it. It's not going to break. What does it feel like? It's hot. Pass it around. Greedy. Alright, so we have a nice reaction going on there. Talk to yours about what kind of reaction. Keep passing it around. Keep passing it around. All right, so here's my picture. My picture is, I hope, super funny. I just love hanging out with you, chlorine. Sodium. Oh no, that's just water. What? Where? Dun dun. Dun dun. Dun 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 dun. I'll never forget you. It's a sad story, guys. These are lame. Okay, well, I hope my picture was better than yours. Okay, I got 2 more things for you. You guys don't like a good love story? All right, so I'm actually gonna let's do our lab first. So what you're seeing is that we're talking about solutes dissolving, right? We're talking about why they're dissolving, how they're dissolving, what's the effect of them dissolving, and we're gonna kind of wrap up this at the end, okay? So I'm gonna give you guys 15 minutes in the lab. That's it, and the lab is very, very easy. You're basically looking at the information of how does sodium chloride, sodium bicarbonate, and sucrose act in solution, and then we're going to kind of come up with some plans, because next week we're going to make snow globes. You need to bring in baby food jars, not pickle jars, not mason jars, or small like baby food jars or small mason jars, because this requires a lot of solution, and I got like 70 people to serve, so little jars, glass jars with tight-fitting lid. Write that down, make a note in your calendar, make a note on your phone. But go ahead and get a piece of paper out, call it Solubility Lab. We are moving to the back in our science, in our science in a box groups. And so you got to stay in your science in a box groups for another week, or right this week, because we're working on those together. When you get to the lab, you're going to read the introduction, you're going to draw the data table, you're going to move quickly, you're going to need test tubes, and Justin and I are going to help pass the materials. But like I said, 15 minutes, here we go, on the clock. The lab is in your little bucket. The lab is in your bucket. What's my super-saturated solution? Super-saturated. Let's go. The lab is in your bucket. Alright, quickly, you are getting your test tubes out. You are getting your baby oil, and you are getting your water. Justin and I are bringing you sucrose. You need your own stuff. Be careful. Cut your fingers.
I don't know. I really don't know.
One person should be filling up the test tubes with baby oil, not filling, but what it says in the lab. And then one should be filling the other test tubes with water if you would like to go Now, you might have to Hey guys, actually, I have maybe a little bit of a better idea. If you are at a group that, listen, if you're at a group where you have a group right across from you, one of you guys can do the baby oil. So one of you guys can do the water. That way you don't have to worry about quickly moving, okay? So Lindsay's group and Jillian's group, you guys choose baby oil and then vice versa. Yeah. Have you guys got baby oil in there? Let's do that. Let's share results. Share results.
And also the analysis questions aren't hard. They're like stuff that we already know, so I just go ahead and already answer them. Wait, what are we doing?
Yeah, no, we're not going to.
We're not doing the baby oil, they're sharing their water.
Thanks for doing water.
Vegetable oil, bring the pipette to me, and you can gather some vegetable oil from it.
Here, come over to this side, it'll be easier. You don't have to like. That one got me. I say maybe you want to add some more to it.
All right, guys, you should be making observations at this point about all of the solutions you made. Timer's going off in 2 minutes. Are you all sure thing?
None of it did except for the last one. Yeah, all of them. I know the way that one turned out was I think we add more and then try it again. Yeah. We're confused about this one. What's it called? Sunk to the bottom. What do you mean? Water. Yeah.
It's kind of differently. It's dissolving differently.
It's really slow.
Right in your Alright guys, that timer means 1, aqueous solutions go down the drain. 2, oil solutions come into the big beaker right here next to Margaret. She's just going to direct you there. So, observations should have been made. Aqueous solutions down the drain. Oil solutions. Oil-based solutions can come to the beaker here. You have to look at them. Your observations should have been made. Clean water brings everything out. You will need soap and water with the oil-based solutions. Clean them out with soap and water.
To clean up this.
Alright, team, bring your results back up here. I'll see you up here in 1 minute. Everything should be clean. Your test tube should be back underneath your station. Test tubes back underneath your station. My next class will finish cleaning, because you know, they'll clean up after you. I just won't tell them it was you. All right, so hopefully you had a chance to observe some of the things that would be relevant to solubility. And on your chart, we're going to recap this together, and you make sure you correct and write down maybe some explanations that go along with it. So thank you for making your way back up here. We're moving back to the lab in about 5 minutes, I hope, because we're going to be doing our independent work, and so you guys have some time with that as well. Okay, so you've got sodium chloride in the baby oil versus the water. Observation, Ayana, which one did you guys observe? Ayana's group. Water. Okay, so what happened then? Give me dissolve or not dissolve? Did not dissolve. Okay. Who had sodium chloride in water? Oh. Sodium chloride in oil? Did not, right? I might contest that. Give me a thumbs up if it dissolved in water. So we're doing this one, okay? Thumbs up if it did, thumbs down if it did not. Okay, so those that did you guys stir it? Did you agitate it? Right, you swirled it around. Okay, so yes, it did dissolve. Or what I said, dissolved or not dissolved, right? So it did dissolve. It should have dissolved, and it did, because the point you should make is that ionic compounds are soluble in polar solvents. That is the point to make your connection there, okay? Who had, you guys tell me, sodium chloride and baby oil, yay or nay? Thumbs up or thumbs down? Thumbs down, okay, great. So it did not dissolve, and so let's talk about the differences here. We have a ionic compound in a non-polar solvent. Those are not similar. They don't like to meet and intermingle with each other, so they don't have strong intermolecular forces. They're not going to dissolve. Okay, sodium bicarbonate, which is your baking soda, and baby oil, yay or nay? Nay. I got like 4 people participating in my survey. Let's go. No. Okay, so it did not dissolve. And why? Can you guys tell me why it didn't? It's ionic. Okay, why wouldn't it dissolve in this one? Right, the non-polar nature of that solvent means that they don't like to dissolve in one another. What about in the polar solvent water, yay or nay? Yay or nay? Give me some thumbs. Yes, okay, great. It did dissolve, and that's because of the nature of the solvent being ionic. I'm sorry, the nature of the solvent being polar, which dissolves really well ionic substances. And so polar molecules have like a partial positive end and a partial negative end, and the ionic compound has a full-on positive and a full-on negative. So we have like total attraction going on here These are both ionic, and they do a great job of attracting to the other opposite end of the molecule of water, whereas this one's just a big fat piece of carbon. There's no partial charges at all, so there's no ability to attract. All right, what about the sucrose? This one might have some varying results. In baby oil, did it dissolve, yay or nay? Most of us, did it change at all? It just kind of stays suspended in there. Got a little stutter there. Okay, so it stays suspended. Okay, so how was that different than water? What did we observe with water? It didn't dissolve 100% in water. Yes or no? No. Okay, what were some observations you guys made? Okay, so I'm going to say some dissolved, but some of it sunk as well. So here's the issue. This is a molecule. It's a polar molecule, but most of it's just a big bunch of carbons and hydrogens. So what you should have noticed is there's a vast difference between how did an ionic compound dissolve and a polar molecule dissolve. The word dissolve is a really cheap way of saying something that goes into solution, but it's not really full of your knowledge of chemistry. The real word we want to use for ionic compounds is not dissolve. We want to say they ionize. Write that down on your chart. I'm writing this down for you so you can help me out here. Okay, so ionic compounds will ionize. Ionic compounds, the second one, will ionize. That means they break into their ions. What property does that give them that's different than most other solutions? If they ionize in water, they can do something really special. Like, you don't drop your hairdryer when you're in the bathtub, right? Those can conduct electricity really well. Really well. Really, really, really well. And sucrose, it just dissolves. It does not do this thing. Why does it not ionize? Think about the differences here. Because it's not ionic. It can't ionize, right? It doesn't even have ions in it. The word is in itself, right? So that's ionic, it ionizes. That's ionic, it ionizes. That's not ionic, doesn't ionize. So can this one conduct electricity if we wanted to drop our hairdryer in it? I'd feel safe in a saltwater bath and dropping my hairdryer. Maybe. I wouldn't try this at home. But it's not going to conduct electricity, so it's not conductive. And those solutions have different properties because of the solutes that are going into them. So, this is your brainstorming thought for yourself. Next week we're going to make snow globes. You have to think about what does a snow globe typically need. It needs a little figurine in it, like, you know, it's got to have like some sort of happy thing that's getting snowed on. So what we'll do is we'll get our baby food jars or small jars, and we'll take our jar. The lid's going to be on the bottom. We're going to hot glue a happy person here, okay, whatever your figurine is, and we're going to put our solution in here. But your job is to figure out what your solvent is going to be and what your solute is going to be to make your snow globe. So if you need to write that down for yourself, it's up to you to make it successful. We did a couple of activities to see that so that you would see what dissolves and what doesn't, but there's other things out there that we didn't use. There's like cornstarch, right? That's like kind of powdery. You might need to look at what cornstarch is made of. There's like Epsom salt. Who's ever used Epsom salt? It's just magnesium sulfate, which is an ionic compound. That's probably about it. There's a couple of other white powders out there, the legal ones, so that's all we'll be using. Okay, so let's make a really good snow globe. All right, so the last thing I want to show you is a video, okay? So I want you guys to, this is my favorite video of all time, write down like 2 things you learned, okay? Favorite video in terms of chemistry. I do have a real life outside of chemistry, but it's not very active, so here we go.
We saw you. Nice. Great. Now we're going to get sued by AT&T. The salt is up in water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, same throughout. Homogeneous, same throughout. Solvents that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and unpolar solutes just won't mix, but a non-polar solvent like an E can fix. Like dissolves light, polar and polar. Like dissolves light, non-polar and polar. And all the solvent molecules used up.
You get it?
Look at the solute in your cup. Solutions that...
Did you get it? Oh, I'm not sure you got it. Hold up. Hold up. My favorite of all time.
Like dissolves life.
Polar and polar.
Like dissolves life.
Not polar bears.
Polar and all the solvent molecules used up. Better stuff with the solute ion in your cup. Solution saturated, it is full bore shore. Solubility's been reached for that temperature. Saturation on the line. Saturation on the line. If the still some water molecules unstuck, then more solute can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated. Put more in. Unsaturated. Put more in. If you put more solute in, then you be dissolved. Then a supersaturation situation's involved. The aqueous falls out as a precipitate. But the solution is unstable, so you acetate. Supersaturation. Supersaturation. The salt is not the water in the
Okay.
day.
That's it. I need you to see that, so that kind of brings together all the solution stuff together. All right, so game plan. I have a number of people who need to video. That includes, and I will finish up our notes tomorrow, okay? I had a couple more things to finish, but that's okay. Here's what I'll do. You either are going to do one, actually I got a couple of people who did not finish the thermodynamics lab yesterday. That's only to page 125. That's probably because you were videoing, right? So you're gonna finish the thermodynamics lab today. If you are videoing, you got to jump on that baby now, but wait it 1 second. If you've already finished the thermodynamic lab and you're not videoing today, you're going to finish the molarity worksheet and then take notes on molarity, and you'll see there's 3 videos under my website for tonight's homework, but we'll recap this at the end. We have 20 minutes, so we got a little behind. So if you were videoing, you better move that booty fast. Okay, go. We're not going to do this part right here. Let me turn the lights on. So goggles on, make sure that you are being effective.
I don't think she realizes that I haven't. And also, we have to put the bowl that we need hot water now, and that's like the way